Assalamualaikum, very good morning. So for today's lecture, we're going to proceed with the second type of EMF generation, which is called as motional EMF. Okay. So for motional EMF, we have learned previously that it is generated by the conditions whereby the circuit is said to be moving, yeah, and the field is a static, yeah, it's a static condition. So as shown here in this diagram, we are having a bar, yeah, a bar which is moving, as shown here, is moving in this direction with the velocity of u, and there is a magnetic field density of B, which is pointing upward, as shown here in the diagram. So by using the right hand rule, yeah, right hand rule, which is the fundamental uh, concept that lead to the generator's working principle. Okay, we know that if we have this kind of circuit, so we are supposed to have a uh, this is the direction of your structure, the moving bar. Okay, and supposedly this will be your field direction, and supposedly your current should be directed in this direction. Okay, so this is the right hand rule, so you can refer to this any literatures that describe the Fleming's right hand rule. So I repeat again that this will be the direction of your moving bar. I mean the moving bar is directed towards this direction. This will be the direction of your field, and this will be the direction of your current, the induced current. So for that, we can say that the current will be induced in this direction as shown here in the diagram. Okay, so that should be the loop of this, the loop whereby the current, the induced current is said to be flowing in this particular circuit. Yeah. Okay, so for now, we're going to proceed with the formulations of equations that govern the motional EMF. Okay, so for this, we're going to start with the magnetic force topics. I mean, magnetic force concept, which has been learned previously. We know that for the magnetic force, we have the equations of dF is equals to I dl cross B. Yeah, this is the basic equation related to this filament current. And if you assume that if this particular moving bar is made up of a volume charge, I mean a structure which consists of the volume current, sorry, the volume current, we can see that this equation will be dF should be then equals to J vector dV cross B. Okay, in which we assume that this particular moving bar is formed by a volume current density, yeah, which is having a J symbol. We have learned this previously, yeah. Okay, and we know that if we have a volume current of J, we can assume that from what we have learned previously in electrostatic, that the charge basically is moving. Yeah, the charge which constitute the current is said to move, in which the equation states that the J basically will be referred to rho V of U, yeah, in which we have the current, the charge amount rho V that is said to move with velocity of U, yeah. So for this, we're going to have the equations down here, whereby the equations of J dV cross B is now written to be rho V U dV cross B. Okay, so this will be the magnetic force that exists, that is actually exists in this particular moving bar. Yeah. Okay, and for that, we have the equations of dF rho VU dV cross B, and we can write that we have a rho V dV. So these terms is basically equivalent to a dQ, a charge. Yeah, and for that, we're going to have the equations of dF equals to dQ of U cross B. Okay, so this is the force that is said to exist towards the charge of dQ in the moving bar structure. Okay, and from what we have learned previously, that the force and the charge is related to this equation. Yeah, where we have this electrostatic field equation. Yeah, electrostatic force equation. We have learned this previously. So we can then relate it to these equations that we have generated, whereby we can have the equations of EM. So EM stands for the motional electric field intensity, and that it should be then equal to U cross B, yeah, which states that the motional electric field intensity will be then equals to the U cross B, which is the velocity of the moving bar cross product with the electric field density. So if we go back to this particular structure, we can see that the motional electric field intensity that is generated inside this moving bar, the EM, yeah, should be then equals to the U, the velocity of the moving bar, cross product with the B, which is the electric field density that is exists, yeah, in this particular structure. So that should be the motional electric field intensity that is said to exist in this moving bar as a result of the moving bar, which is moving in the existence of the electric field density. Yeah. Right. And for this, if we know that now we have the motional electric field intensity term, the EM. So by applying the equations that we have seen in chapter 4, yeah, in chapter 4, whereby we have the equations of potential V equals to closed loop integrations of E dot dl. So this is the equation that we have seen previously in chapter 4 when we are dealing with the electrostatic field intensity of E. But previously, this particular equation is then equals to 0. It is equals to 0 because the E that we have learned previously is related to electrostatic field. But for this particular case, whereby the EM is not electrostatic field, yeah, so the EMF is not 0. Yeah, so the EMF is then equals to this equation of EM dot dl, the closed loop integration of EM dot dl, and by applying that the EM is equals to U cross B, so we are going to have the equation that govern the motional EMF generation, in which the EMF is equals to closed loop integration of U cross B dot dl. So we can then calculate the EMF generated by the motional EMF simply by using this equation. Yeah, right, in which the equation states that the EMF can be generated by any non-zero value, yeah, non-zero value of the velocity of U along the path in motion. Yeah, so for this, I believe that we need to have few examples in order for us to understand better on this concept of motional EMF. So for the first example related to the motional EMF, we are having this particular example whereby we are having the velocity, the loop that we are dealing with is now moving with velocity of U, yeah, as stated here in diagram. So U is moving with velocity of 5y, yeah, 5y. We assume that if this is y direction, y-axis, this is z-axis. So basically, that should be the x-axis, yeah. Okay, so we have the I1, which is given to be 10 ampere. So basically, I1 is a DC current because there is no time variation. So basically, I1 must be a DC current. And the distance between the I1 and the loop is y naught. Yeah. The loop is a square size, 10 centimeter by 10 centimeter, and there are 20 ohm resistor in series exists in the loop. The question is find the I2, which is the generated current. Yeah, generated current inside the loop. Okay, so if we base on this diagram, I2 basically is the generated current, yeah, the induced current, and for the induced current, we can calculate it by simply use the Faraday's law, and we know that from this diagram, this EMF generated is the EMF is generated through the method of motional EMF, because we know that for motional EMF, the current is a steady current or a DC current, whereas the circuit is said to move. So this is a case whereby the EMF is generated by the motional EMF. So for motional EMF, we have seen previously that EMF can be calculated by simply based on the equations of U cross B dot dl. This will be the equation that shall be applied. And if we base on this, if we base on this loop, we can divide the loop into 4 different sides. We have side number 1, side number 2, side number 3, and side number 4. Okay, so the closed loop integration will need to consider all of these sides, in which we can write that this equation of u cross b dot dl closed loop integration shall be then returned to be u cross b dot dl for side number 1 plus u cross b dot dl for side number 2 plus u cross b dot dl for side number 3, and finally the u cross b dot dl for side number 4. Okay, so these are the equations that shall be applied in calculating the EMF, the motion EMF. So let's have a look for the first side, number 1, from 1 to 2. Yeah, for this particular side. We can see that the U basically, for side number 1, okay, we have U cross B dot dl, okay, in which we have U just now is given by 5 of Y, and B can be calculated from this I1. So we knowing that I1 is a filament current which is infinite in length, because we're not given any condition on the length of I1 current. So we assume that the I1 current is having an infinite length. So for that, we can write that the B vector should be written as B as mu naught of I1, which is 10 ampere divided by 2 pi of Y. Yeah, and by using the right hand rule, we can write that your field should be in this direction. Yeah, should be in that direction. So if we base on the loop location, we can say that the direction for the B, direction for the field density will be towards the negative X direction. Yeah, because X it is in this direction. So the field is pointing inward. So the direction for the B field should be in the negative X direction. Yeah. Well, the DL should be dz of Z, because we are dealing with side 1 to 2, which is the DL will be dz of Z. And if we base on the distance between the I1 and the side 1 to 2, we can write that the distance will be Y naught plus 10. So for this, we can rewrite the Y to be equals to Y naught plus 10. So that should be the distance, yeah, between the I1 current and the side number 1. Okay, so let us proceed with the integration here with the cross product first. So we're going to have mu naught of 50 divided by 2 pi Y naught plus 10. Okay, so we have the integration. So Y cross negative X will be positive Z. Okay, so dot with dz of Z basically. So we're going to have the integration of a dz. So we just put it for the length, which is from 0 to 0.1 centimeter. Okay, from 0 to 0.1 meter, sorry. And for that, we're going to have mu naught times 50 divided by 2 pi Y naught plus 10. And that will give us 0.1. And as such, we're going to have mu naught 5 divided by 2 pi Y naught plus 10. So that should be the EMF generated in volt unit. This is due to side number 1. Yeah. Okay, for side number 2, okay, which is down here, we are going to have, yeah, if I can write it here, number 2, we're going to have U cross B dot dl. Okay, so that will give us U will be 5 of Y still, whereas for the B we need to write it as mu naught 10 over 2 pi of Y, direction of negative X. Okay, so for side number 2, I'm taking Y as a variable, because for side number 2, the perpendicular distance from I1 to side number 2 can be from 0.2 to 0.3. So this is a variable. So I just put y as a variable, yeah, and then we're going to have it this dot product with the dz of z. Okay, sorry, not dz of z. I apologize, because for side number 2, the dl will be if we base on this diagram, yeah, so the dl for side number 2 will be equals to dy of y, yeah, the dl will be equals to dy of y. That should be the dl for side number 2. So as such, we're going to have the dl for side number 2 will be dy of y. And if we base on this, we can see that for the cross product, y cross x will give a z direction. And when the z direction dot with y, so this will lead us to 0 value. So there is no contribution of EMF for side number 2. And similarly, this can be expected for side number 3. Sorry, side number 4. Yeah, side number 4, because side number 2 and side number 4 are equivalent in terms of its nature. So we can see that for side number 4, the EMF will also be 0. Yeah. Okay, so we're left with the third side. So for the third side, it's almost similar with side number 1, except that the perpendicular distance will be y0 only. Yeah, for side number 3, yeah, the perpendicular distance will be y0 only, as opposed to side number 1, which is y0 plus 10. Yeah, so that's really the only difference. And for that, we're going to have u cross b dot dl. So we're going to have u cross b dot dl. Okay, and then we're going to have 5 of y cross product with the b, which is mu naught times 10 over 2 pi of y naught of negative x direction. Okay, and the dl will be dz of z. So if we proceed with the calculation, we're going to have it as mu naught 50 over 2 pi of y naught. Okay, and for this, we're going to have it as integration of dz, which is from 0 to 0.02 again, yeah. So then we're going to have it as mu naught 50 times 0.02 divided by it's 0.01, 0.1, sorry, 0.1, my mistake, sorry for that. Okay, so it should be 0.1. Okay, so we can have it as 0.1 to 0.0.1, so that I have 50 over 2 pi y naught multiplied with 0.1. So this will give us mu naught times 5 over 2 pi of y naught in both units. Okay then, yeah. That will be your EMF. I think I made a mistake here. Sorry for that. For side number one, basically the integration must be from 0.1 to 0. Yeah. So because we are dealing with the current direction. Okay. So it should be from 0.1 to 0. I made a mistake here. That should be 0. And now we're going to have negative. So that should be a negative. Yeah. Negative the value of this. So for this, we can see that the EMF generated, the total EMF will be simply the contribution from side 1 plus side 3. So that will give us mu naught 5 over 2 pi, yeah, 1 over y naught minus 1 over y naught plus 10. So that should be your EMF generated by this particular loop. Yeah, by this particular loop. So for that, we can simply find the I2. Yeah, because once you have the EMF in volt, you can find the current that is flowing in your circuit simply by based on the equation that I2 will be equals to the EMF divided by resistance in total, which is 20 ohm. So I think you can proceed with this calculation of current of I2, in which the EMF has been calculated here. That should be the generated EMF. So the ratio between the generated EMF and the resistors in your circuit will give us the amount of current that are flowing in your right square loop in the problems before, yeah, in this particular examples here. Yeah, so that should be the current in ampere unit. Right. So let's have a look at these examples here. Again, we are dealing with the motion EMF for this example. We are having a square loop of A, B, C, D as given here in the diagram. Okay, so the square loop is having a dimension. I can say it's a rectangular loop, sorry, it's a rectangular loop, ABCD, because the AB is having a distance of 0.02, whereas the BC is 0.03 meters. So this loop is said to be immersed in a uniform magnetic field B, yeah, of 0.5 of y direction. Okay, the side CD of the loop cuts the flux line at the angular frequency of 120 pi radian per second. Okay, which means that your omega is equals to 125, the angular frequency, yeah, radian per second unit. If the loop lies in the YZ plane at time t equal to 0, so YZ plane is here, yeah, at time t equal to 0, determine the induced EMF at t equals to 1 milliseconds. Okay, so we are given the B. B is said to be a static field because there is no time variation. Yeah, B is a static field. Okay, and the loop is moving. Yeah, the loop is moving. So when the loop is moving and your field is a static field, so this is considered to be a motional EMF concept or motional EMF principle. Yeah. Okay, so the question is, based on the given problems, determine the induced EMF at time t equals to 1 millisecond. Yeah, induced EMF at time t equals to 1 milliseconds. Okay, so again, from the EMF, motion EMF, we can write that the EMF to be equal to closed loop integration of U cross B dot dl. Okay, and we know that this U basically is a linear velocity, but from what we have here, the magnetic field, I mean this particular loop is said to cut the flux line at the angular frequency of 120 pi, in which the omega is 120 pi. So the angular velocity and the linear velocity is basically related by the equations of u equals to r omega. Okay, and from here we can write that u will be then equals to r. So r equals to the radius is 0.02. Yeah, because CD is having a distance of 0.03 from the z-axis. So your r basically will be 0.03. So I just put that r will be 0.03. This is for side CD. Yeah, sorry. Let me recall it back. Okay, let me read it back. So basically for U cross B dot DL, we have 4 sides: side number 1, side number 2, side number 3, and side number 4. So this can be then written as U cross B dot DL for side number 1 plus U cross B dot DL for side number 2, okay, plus U cross B dot DL for side number 3, and then we have U cross B dot DL for side number 4. Okay, so we have the U cross B dot DL for all of these 4 sides, 1, 2, 3, and 4. Okay, so we are dealing with side number 1 first. So for side number 1 is what I mentioned just now. It's about the U, which is a linear velocity. So you know that for side number 1, the distance from the z-axis are 0.03. So r for side number 1 here will be 0.03. For side number 1 then, yeah, we're going to have that U will be R, which is 0.03 meters. Omega is 120 pi. Okay, and knowing that the omega is directed in direction, so your U will be directed towards positive V direction. Okay, and cross product with the B, and we are given that B is 0.5 of Y direction. Okay, and then it should be then dot product with the DL. dl will be the vector for side CD. So side CD will be having a dl of dz, direction of z. Okay, so that should be your u cross b dot dl for side number 1, yeah, which is for CD. Okay, but looking at this, we know that we are having a cross product between phi and y. So what we need to do now is that we need to transform the phi unit vector into Cartesian. Yeah, the phi unit vector need to be transformed into Cartesian, in which we can write that the phi, yeah, the phi unit vector should be then equals to negative sign of phi, direction of x, plus cos of phi, direction of y. Yeah, so that should be a transformation for unit vector of phi with regard to the Cartesian x and y unit vector. So for that, we are going to have 0.03 multiplied with 125, which will give us 3.6 of pi. Okay, so phi will be negative sine phi of x plus cos phi of y, cross product with a negative, sorry, with a 0.5 y. Okay, and this we then dot product with a dz of z. Okay, so if we base on this, we can see that the terms of cos phi of y will be cancelled out because cross product with this y direction will give us 0. So we only have a cross product between x unit vector and the y unit vector, in which this will give us integrations of negative negative 3.6 pi multiplied with 0.5, in which this value will give us negative 5.6548. Okay, and then we're going to have a sine of phi, right? So x cross y will give us z of z and dot product with dz of z. So end up we are going to have so if I can bring it down here, okay, bring it down here. So we're going to have a EMF for side number 1 will be equals to negative 5.6548 integration. Sorry, sine phi is up. We take it out here. So we're going to have integrations of dz, okay, which is from 0.00 to 0.02. Okay, so that should be the z integration, and end up going to have negative 5.6548 multiplied with 0.02 in sine of phi. Okay, so for this, we're going to have the value of negative 0.113 sine of phi. So that should be the value of EMF generated by side 1, which is from C to D. Okay, for side 2 and 4, okay, side 2 and 4, I think you can prove on your own that for side 2 and 4, the value of EMF contributed will be 0. Yeah, the value of EMF contributed will be 0 because the argument for this is similar to the previous example that we have solved just now, that due to the dot product between different new vectors, you can prove this on your own, yeah, that for side 2 and side 4, the value for EMF, I can write it here, for side 2 and side 4, the value of EMF will be equal to 0. Yeah, you can prove this on your own, yeah. Whereas for side number 3, we can see that the value of U will be 0. Yeah, the value of U will be 0 for side number 3. Okay, because the R, the radius is 0. Yes, side number 3 is located at the z-axis, on the z-axis. So due to that, we can say the radius of R will be 0. So as such, again, there should be no contribution of EMF from side number 3. So end up, we are going to have only contribution from side number 1 that will for this particular structure. Yeah, whereas for side number 2, set number 3 and set number 4, the contributed EMF will be 0. Okay, so we then proceed with this EMF for set number 1. So I just write it for you again. So for set number 1, the EMF generated will be then equals to negative 0.113 sine of phi. Okay, so the question now is how we can define the phi then. Okay, so we know that the omega, yeah, the angular frequency basically can be defined by the ratio, differentiation, yeah, by the differentiation of the angle phi respect to t. So that should be how we define this angular frequency, yeah, the angle with regard to time. So from here, we can write that the angle will be then written as omega t plus c, yeah, when we integrate left and right, going to get these terms that relate to frequency omega and also the angle of phi. And if we base on this information that state that in the YZ plane, the time t is 0. So YZ plane is here, yeah, YZ plane is here, the time t is 0, which means that at YZ plane, okay, YZ plane, your phi angle is equal to pi over 2. And at that particular angle, pi over 2 times t is 0. So for this, we can write that your c, the constant of c, basically will be equals to pi over 2 because t is 0, which will then give us that c, the constant will be equals to pi over 2, in which from here we can write that your phi angle is equal to omega t plus pi over 2. So for this, we can write that the EMF is equals to negative 0.113 sine of omega t plus pi over 2. Okay, in which from here we can rewrite it as equals to negative 0.113 cosine of omega t. Okay, so this will be the EMF that is to be based on time. Yeah, EMF which is based on time and also on the omega. So we can write this as 0.113 cosine of 120 pi of t. Okay, so this is the EMF terms that is based on time, and we can then use it to answer question 1 here, yeah, which is to obtain the EMF, induced EMF at time t of 1 millisecond. So as such, we can write that at t equals to 1 millisecond, okay, we can have that the EMF will be equals to negative 0.113 cosine of 120 pi multiplied with 1 times 10 of negative 3. So please write the please get the answer, which will be in volts unit. Yeah. Okay. And for part 2, which is to find the induced current at t equals to 3 milliseconds. Okay. So knowing that for this particular loop, yeah, we have the resistance of 1 ohm, So at 3 milliseconds, okay, if I carry it here, sorry, so at 3 milliseconds, okay, so we have the EMF generated will be negative 0.113 cosine of 120 pi multiplied with 3 milliseconds. Okay, so we can say that the current induced at 3 milliseconds, okay, I will be equals to EMF that we have here, negative 0.113 cosine of 120 pi multiplied with 3 milliseconds, 3 times 10 of negative 3 divided by resistance, which is 1 ohm. So then we're going to have the current in ampere. So that should be the current that is said to flow in your circuit, in your loop at 3 milliseconds by simply calculating the EMF. And from the EMF obtained, you need to divide with the resistance in the circuit, and then it will give us the current that is said to propagate in your circuit.